Class, this is your teacher speaking to you. Yes, this is day 2 of the Phantom, a mystery teacher coming through the walls. I hope that by today you got to know yourself yesterday, you're treating with even more respect today, and I am hopeful and pretty confident that you're glad you're not looking at me, because I'm glad you're all not staring at me. It's typically kind of an awkward thing for me, but I make do because I like to chuckle and laugh at different people in the class. Brennan, yes, I am talking about you in the back there, but I think you'll make do. So today, our main goal is to continue on talking about force diagrams, really starting to look at balanced, unbalanced systems. What does that mean? What is that telling us? How do we draw this picture and interpret what's happening around it? It's going to be quite a bit shorter notes than yesterday, which I'm guessing a lot of you are fist pumping and excited about. Then we'll get some more work time to finish up a new worksheet on balanced, unbalanced systems. And then also get time to finish up, if you did not finish the weight lab you started yesterday, the supplies are still up front, and the worksheet that was attached to that. Don't forget, since I am not here, that you can come on up and use this physics answer key up front here. Make sure that you're checking your answers, you're understanding the material. Please make sure you're keeping up in the textbook. There's some good readings in there with information being reinforced, along with different types of questions that can be asked on that. So pay attention to your calendar. Make sure you're keeping up on the bookwork. Hang with me here while we go through a couple more notes for today. So, question for today then is draw a force diagram that correctly illustrates a car driving on the freeway with the cruise control on. Now, yes, some of you, I realize, have never used your cruise control. You don't know where it is. I've driven behind you. But there is a button on your car for the cruise, and there's a particular purpose for it. So why don't you go ahead and draw a force diagram of your car, of what it looks like when your cruise control is on. Go ahead and get started, and I will start working through the problem shortly. All right, the thing with the problem, yes, I heard Tyler talking in the back, and he thinks that there isn't a cruise control button, or we're really not sure what he's useful for, but I'm confident his car has one. So let's take a look at what this is. So if I have my beautiful drawing of my road, it's a green road because we're driving on the grass, which some of you think is something you should do. You shouldn't be driving on the grass. You try to keep it on the road at all points of time. But in this case, we have a green road. So we have a green road. I have some super sweet, all making black tires, not blue tires. I was going to make them blue tires, but then we'd have to look at Vogel's car here on campus, and some of us like that, some of us don't. So here we go. Here's my beautiful box car. Maybe we'll put a little windshield in the front of it like a bus, which we all wish we could drive a school bus as we were going places. And yeah, let's put some seats in here just for fun. It's a convertible, really ugly looking convertible, but hey, here's the car. So it's driving down the road at a cruise control, with the cruise control on. So what does that mean to us? Well, yesterday we talked about a couple key forces that hopefully we can still figure out exist today. So one of them that I'm hoping you can just spring to mind that hasn't disappeared all of a sudden, even though Allie sometimes thinks that gravity doesn't exist, it does exist. And so we have gravity pushing us, well, hopefully we can still remember, into the ground, so we'll label the force of gravity. And as we're thinking about, well, the force of gravity, I know that when my car is driving down the road with the cruise control on, I am not sinking through the ground. So something else must be happening. Well, yesterday we learned about this force called the normal force. Normal force is perpendicular to the contact surface. Now, if our green line here is our road, yes, your tires should be in contact with your road at hopefully all points in time. And so our contact force is perpendicular, which means that's in that direction. Now, if you take a look at my arrows, since I know my car isn't sinking through the ground, I'm not driving through the grass, through the snow. I am actually driving on a road, hopefully with the cruise control on. I can confidently say then that the length of my arrows for my gravity hopefully is the same length of the arrow for my normal force. Equal and opposite forces, no hovering cars, no sinking cars. Yeah. Then if I'm on the road, I know that my car hopefully has an engine to it, and the engine hopefully likes to create and push me forward. So some of you need to work on your whole backwards driving skills. But in this case, we're going to be driving forward with the cruise control on, because I have never personally driven backwards with my cruise control on, which I would not encourage you to try. So we have our cruise control, our motor pushing us forward, and so we're going to say force of the motor. Now I also know that as I drive down the road, especially in a convertible or anything, I stick my hand outside of it and shoo, my hand gets hit or pushed backwards by air molecules. And so I know that there is a ton of force pushing on the front of my windshield. We call this wind resistance, air resistance. I also know that my tires are touching the ground, so there is some friction taking place. We're going to combine that all together and say it's the force of friction. Because really, wind resistance is a type of friction. It is resisting the motion or the direction that I'm going in. So if I look at this the way I have it drawn, if I asked you what my total force was, what would it be? Well, me being the guy who likes to show all my work for everything here, I would say, okay, well, let's add up all of my forces in the y direction. And if I do that, we'll just call positive up, negative down. I don't know what the number is, but I know they're equal and opposite. So let's just say 10 and 10 newtons for both of these. So it'd be a positive 10 newtons plus a negative 10 newtons gives me 0 newtons of the total force in my y direction. Think through that logically. Is my car changing directions or changing motion speed-wise in my vertical direction? Well, hopefully I'm not hovering my car through the air, and hopefully it's not sinking to the ground. So having a total force in your y direction of 0 should hopefully make sense. Now let's take a look at my x direction. So if I take a look at my x direction over here, and I want to add up everything that's happening force-wise in my x direction, I see that I have a frictional force here in blue and a force from the motor here in red. My arrows look like they're equal in length, but they're pointed in opposite directions. So let's just call this 20 newtons forward and 20 newtons backwards. I like to call forward the positive and backwards the negative. So my blue is going to be my directional pieces here. And if we take a look at that and I add them up, I would have positive 20 newtons from my motor plus a negative 20 newtons from my frictional force, or wind resistance and friction of the ground, giving me a total of 0 newtons. So if I want to look at my total forces in the y direction, I see it's 0 newtons. Looking at my total forces in the x direction, I see it's 0 newtons. And that tends to make me think about, is this realistic? Is this practical? Is it possible if my car is moving down the road still? So ask yourself that question. Is it possible to have perfectly balanced forces or a total force of 0 and have you be moving? As you ponder, I can look around the room and see different light bulbs going off in your brains, I hope, or that kind of mystical look of, really, I don't even know what you're asking me, Mr. Ellis. Well, what this is looking at then, I almost wrote on the whiteboard and not on my smartboard, so that would have been hard for you to see. What we're taking a look at then, well, is this possible? Well, if my total force in all directions is 0 newtons, in the x direction equals 0 newtons. And I know that force, looking at a total force as a mass times an acceleration, if that has to equal 0, is it possible for this to happen? Well, I know that my mass can never equal 0 because the stuff that is in you can't just disappear, otherwise you don't exist and the whole problem doesn't make any sense. So that would have to tell me that my acceleration is 0. Sorry, is 0. I had to cross it out. I don't know. Acceleration equals 0. Is it possible to move with an acceleration of 0? Possible to move with an acceleration of 0. Now, to me, being the nerd that I know that I am, I start thinking about mathematical definitions. Well, acceleration equals the change in velocity all over the change in time. I know time has to continue on, and so let's take a look at this idea of change in velocity. Well, what is velocity again? There are two main components. Oh, I think I heard Steckman say one of the components, yes, I know, it was Steckman, I'm confident in that. He said that one of the components of velocity is a directional piece. So can you move and not change your direction? Oh, I heard Steckman again, he said, yes. So yes, you can move and not change your directional piece. The second component of that being a vector, if we have a direction, is a speed, right? Because speed plus direction equals velocity. So can you travel and not change your speed? Hopefully. There's a resounding yes. So if you can drive and not change directions and not change your speed, then it is possible to drive with your acceleration at 0, having a balanced system, which is actually the entire point of cruise control. Because when you're pushing your pedal, called the accelerator, or pushing your brake, which is also an accelerator, it either takes away from your speed, changing it, or when you push your gas pedal again, it causes you to accelerate, which means the engine works harder. Anytime the engine has to work more, create more force, it uses more gas. The cruise control's point is to save you money on gas, to try to create a balanced system so the engine in the car can relax. It doesn't have to work harder. It can just balance forces. If you're balancing forces and your engines are working less, you're using less gas. If you're using less gas, you're getting better gas mileage. If you're getting less gas mileage, you actually have money in your pocket, which I do not and wish I had. So is this practical? Yes. It is the purpose of the cruise control in your car. So, with that being stated, in a nice, long, winded way here, we are going to take a look at the problem from yesterday. The problem from yesterday that we had is like right here on the board. So let me see if this is going to work. And we said Chad is driving his truck from Andover High School to Goodrich Field to watch the Tornadoes lose to the Huskies on a windy Friday night football game. The truck's engine is pushing the truck down the road with a force of 50 newtons. The headwind that night had a force of 35 newtons, and the trailer he was pulling with his four-wheelers in it, yes, we are in Andover, pulling it with his four-wheelers, force of 15 newtons in the direction of the wind. What was the total force? And my question then to you yesterday was, is this possible if the truck is moving? So quickly, I'm going to draw my force diagram. I have this super sweet truck with huge wheels on it, itty bitty little body frame, right? Yeah, I don't know what kind of truck this is, but it's my sweet truck, right? And then it's attached to a trailer on little itty bitty wheels, because we never lift our trailers, with some four-wheelers in the back. I know that the engine of my car is pushing my truck down the road with 50 newtons, so hopefully we're driving forward at that pace. And I know wind is hitting the front of my truck with 35 newtons, so notice how my vector, my magnitude, the length of my arrow is smaller, but it's in the opposite direction. And I know that the trailer that's behind it is causing some more friction. It is pulling backwards at about 15 newtons. So there's my force diagram. So now let's add up all my forces in, we only have one direction here, the x direction. Because we can clearly see that, hey, if this is the ground, downward we're going to have the force of gravity, which you cannot see, and I'm writing. And upward, we can confidently say, well, there's a contact force, so I have my normal force. My y direction is going to be balanced because my truck does not hover throughout the air nor sink through the ground on a paved road. But look at your x direction. So we're going to have positive be forward, negative be backward, because that's easier for my brain. I have a 50 newtons in the positive direction, plus a negative 35 newtons, because I'm adding them all up, plus a negative 15 newtons, gives me a total of, hopefully we found this yesterday, 0 newtons. So now the question is this possible? The truck is moving. And I hope that you're all standing on your chairs saying, yes, Mr. Rose, it is! Because it is possible. Because we talked just about that if its force is 0, that means mass times acceleration is 0, which means acceleration is 0. And can you drive with an acceleration of 0? Yes! It tells you that your direction isn't changing and your speed isn't changing. So one scenario is you are completely stopped, so you have no speed, and therefore you have no direction. If you stay stationary, it is stopped. Here it says the truck is moving, so what does that tell us? Well, the direction cannot change, and the speed cannot change. Still possible, just two totally different scenarios. Acceleration of 0 can mean you're stopped. Acceleration of 0 can mean you're traveling in a constant direction at a constant speed. So yes, this is possible. Leads us to the idea of if total forces of something is 0 newtons, we will call this system balanced. Okay? So taking a look at your balanced system here. Oh, is it going to work? Okay, good. Balanced forces tells you a couple things. One, forces on an object that are opposite in direction and, key thing is, and equal in size. So those two components have to be true. If that is true in your x direction, it can be balanced in your x direction. If it's true in your y direction, it can be balanced in your y direction. If it's true total, we call that a completely balanced system. A completely balanced system tells us that there is no change in your velocity or the motion of the object. Why again? Well, because of F equals ma, and force is 0, mass times acceleration. Acceleration must be 0, and acceleration is the change in velocity all over the change in time. And I've repeated myself so many times here just to make sure we're clarifying that point. A balanced system tells us whatever is happening motion-wise, will not change. Because force, we learned, the definition of it that we talked about, is anything that influences the change in motion. So if your motion isn't changing, your forces are 0. And I know that that leads us into what we're eventually going to talk about, and you all are so excited about, is Newton's first law. Because Newton's second law, F equals ma, also helps us define, prove, and show Newton's first law. So today in your worksheet, you're going to be looking at balanced and unbalanced systems. If it's unbalanced, you should be able to calculate a total force by now. If it is a balanced system, well, you had to calculate a total force and find that it's 0. And if it's a balanced system, it tells you some very specific information. that you need to start applying to the problems or to the scenarios at hand. So that's what I got for you today. I feel like I walked around the room a ton, so hopefully my voice volume is not too bad. I got all animated and acted it out to an audience that doesn't care because there's no one here, because I know that if I was here, you would care. And I also know that deep in your heads, you're like, Mr. Ellis, just shut up so we can work. And so I'm going to. Your sub's going to hand you the worksheet. She's going to let you get going. Please give her the utmost respect for the rest of the hour. Make sure you're checking your answers and finishing up any other book work when you get done. Thanks for your time, and get excited to listen to my annoying voice again tomorrow. So, with that being said, I got to figure out how to stop this thing since we are no longer in smart software, and I have to walk over to my desk. We're discarding that since you have it. Oh, it's not what I wanted. There it is. Goodbye. Good night. Have a good day.